Alright, welcome back to another exam explain question. We are looking at the 2016 Victorian paper, question 18, on interference patterns. Now we have two experimentalists that conduct an experiment to study interference using a laser and a double slit. Now, when we have a double slit experiment, we will have these bright bands. So bright bands usually denoted as n equals to 0, or the center one, and then we have destructive interference with the dark bands, and then obviously the bright bands is constructive interference. Okay, it says that the path difference dictated by delta S1 to X, so X is this dark band here. We're saying that the light ray from the laser goes to S, and this source of light moves to X here. So that's one of the pathways. We're saying that also it will connect with path S2X, which is this one here. And when these two rays of light combine, or two waves of light combine, you get a destructive interference. So we have destructive interference here. Okay, so there's that. Now, breaking it apart again, let's look at what the question's asking us. It says calculate the wavelength of our laser. Okay, now the standard formula we use to find constructive, destructive interference, analyzing any type of interference patterns, is N, so which order, which fringe are we looking at, lambda, wavelength of the source you use, and D, which is our slit separation, sine theta. Okay, now as you can see in this formula here, it does not include path difference. So how do we find path difference? Well, have a look here. The actual difference in how far one light wave has to travel compared to another is this part here. This is delta, okay? And obviously this is just an imaginary addition. So we draw it like so, okay? Drawn like so. Alright, now we know what D is. It's this length here. This we're going to call angle theta, and we're going to assume this ray. So if we draw an imaginary line from the first light wave, a normal line down to the second wave, it's going to form a right angle triangle. Okay, so if sine theta is the angle in which the different, or sine theta is the angular difference between S1 and S2, you can write down that sine theta, that particular angle difference, is given as opposite over hypotenuse. So the opposite side here is delta, our path difference, and divided by D, our path separation. Or slit separation, sorry. So we have path difference, and we also have slit separation. Okay, so there's that. So the formula I'm dealing with can also say that the path difference will influence whether or not I get a constructive or destructive interference. That's a key point there. Okay, let's try and calculate the wavelength of the laser we use. Okay, so based on this formula that I've just written out, I can see that path difference is equal to n times lambda. Okay, now I know what the path difference is, 750 nanometers. Remember, nanometers is 10 to the minus 9 meters. So let's substitute that in. 750, 10 to the minus 9 meters equals to n. Okay, so we know that the center band is 0. We know that the next constructive interference band after that is 1, so a new integer. We also know that for destructive interference, the waves must have met at half the wavelength of each other. So if we have one wave coming like so, we have another wave coming like so. So we actually know that at x, we are dealing with 1.5. So the wavelengths are moving out of phase 180 degrees of each other. So n in this case is 1.5 lambda. Right, so let's divide it over to the other side. So lambda is 750 10 to the minus 9 over 1.5. And let's check out what answer we get. Okay, so you should get, in this scenario here, an answer which is 5 times 10 to the power of 5 meters. Okay, so the wavelength we use is about 5 times 10 to the minus 7 meters. That's about 500 nanometers. So about 500 nanometers. So we're dealing with something sort of on the blue-green spectra of light. And then in question B it says P is a bright band, so that's on our diagram there. Calculate the path difference S2P, S1P, showing your working. Okay, so I use a different color. Actually, let's keep with red. P is over here, so S1 or S2 and S1 traveling to P. So P is our second bright fringe or band, whichever word you like to use. Okay, so again we're going to substitute it back into the same equation. This time we'll use a different color. Okay, so I know that. So I'm trying to find this. I'm trying to find path difference. But I do know what n is. N is 2. Lambda is 500 nanometers. Okay? Let's do our substitution. So delta equals to 2 times 500 nanometers. And that gives us 1 times 10 to the power minus 6 meters. Okay? So that's what we have there. Next question, question C. So we have replaced the double slit with a single slit. This has a width of W, so imaginary width here we're dealing with. As shown in figure 23, so that's our diagram down here. They find that the width of the central maximum, so if it's the central maximum, it means n is equal to 0, of the diffraction pattern is y. So that's how wide the center max is. They replace the single slit with another single slit of width 2w. Identify the diffraction pattern that Amelia and Rajesh will observe. Explain your answer. Okay, so we do know that the diffraction, so the width of diffraction, let's call it y, is equal to the wavelength you use, okay, divided by the width of the actual slit. Okay? So, if I increase, and assuming wavelength is constant, so wavelength is constant, let lambda be 1, so which is dealing with the constant here. So, as diffraction, we have doubled the width. That would mean, proportional to, sorry. So, if we doubled the width, therefore diffraction width will become smaller. Okay, because we know the proportionality between the two. If the diffraction pattern was, if we were to increase the wavelength, then we'll increase the width of the diffraction. But because we have increased the width separating the slit, so the gap, we actually make the diffraction pattern wider. So diffraction width will become wider. Another way of saying it, so width of the diffraction pattern will decrease by a half. And the reason why that's the case is because we know that the width of the diffraction pattern is inversely proportional to the width of the slit. Okay? That's how you explain the question there.